Welcome, this is Dr. Plague. Today I'm going to go over the math involved with the 555 timer formulas, and I'll be deriving those formulas from scratch. I've decided to break this up into two videos so they don't get too long. After all, who wants to watch really long videos on math? There are 5 formulas from my Fun with a 555 timer video that I would like to derive, and they are the time low formula, the time high formula, the initial time high formula, the time high formula for the diode circuit, and the new time low formula with R3 added into the discharge line. In this video, I will be covering the first 4 of those formulas, and I'll leave the last one to another video since that one will involve a Laplace transform. So, get your math hats on, and I will see you at the whiteboard. So, before we get started, there are some fundamental mathematical relationships that anyone involved with electronics should be familiar with. You should be familiar with Ohm's law, which states that the current through a conductor between 2 points is directly proportional to the voltage across the 2 points. The basic formula for Ohm's law is V equals IR, with V being voltage, I is current, and R is resistance. I like to draw it in a circle like this. If you're looking for voltage, it's I times R. Current is V divided by R, and resistance is V divided by I. Excellent. Now, you should also know the formula for current through a capacitor. It is C dV dt, which means it is capacitance times the rate of change of the voltage across the capacitor with respect to time. Hopefully, you are a little familiar with calculus, and if not, you can use a calculator. These should be the only basic formulas we will need today.
I can see that this will be the perfect video to help put me to sleep.
Just wait till part 2 comes out. So, let's start with the first formula, which was time low equals the natural log of 2 times R2 times C. Now, let's see if we can set this problem up. The time low occurs when the capacitor is discharging to ground through R2. When the output is low, the discharge pin is pulled to ground, which grounds the node between R1 and R2. Therefore, we don't need to worry about R1 since one side of it is tied to VCC and the other side is tied to ground. We are left with a capacitor tied to R2 on one side and grounded on the other side. R2 is also grounded on one side. We can consider the threshold and trigger pins on the 555 as high impedance inputs. Therefore, we don't need to worry about their effect in the circuit. Because of this, we can redraw the time low circuit like this, where R represents R2 and V is the instantaneous voltage across the capacitor. Remember, the capacitor starts to discharge when its voltage reaches 2/3 VCC and continues to discharge until it reaches 1/3 VCC. Kirchhoff's current law tells us that the sum of all currents entering and leaving a junction must equal 0. Let's use the ground node as our junction for Kirchhoff's current law. Remember that the current through a capacitor is C dV dt, and by using conventional current flow, it flows from positive to negative. Ohm's law states that the current through a resistor is the voltage across it divided by its resistance, again from positive to negative. So, by using Kirchhoff's current law, we can say that C dV dt plus V over R is equal to 0. Now we have the problem set up, so let's solve it. What we have here is a differential equation, and the first thing I want to do is to separate the variables, which are V and T, voltage and time. So first, I'll subtract V over R from both sides. Next, I'll divide each side by C. Now, I'll multiply each side by dt. Then, I'll divide each side by V. Now, all the V's are on the left side and all the T's are on the right side of the equation. Now, what I want to do is to integrate both sides, so we'll use a little calculus. R and C are constants, so we can pull them out of the integral. If you know your calculus, then you will know that the integral of 1 over V dV is the natural log of the absolute value of V. If you don't know your calculus, then you can use a calculator such as the TI-89, and you can see it gives us the same result. And in our case, the voltage will always be positive, so I'll just get rid of the absolute value bars. The integral of dt is just t, so we have negative t over RC. And we can't forget our constant of integration, which I'll denote as k. Now I want to solve for v, and notice that v is within a natural log. So I'm going to use the inverse function of the natural log function, which is e to the x. So I'll raise e to the value of each side of the equation. Since e is the inverse of natural log, the left side of the equation becomes v. Using the product of power rule, we can change the right side to e to the negative t over rc times e to the k. And we can say that e to the k is just some constant k. At time t equals 0, e to the negative t over rc is equal to 1. So we can say k is equal to the initial voltage. And we get v of t equal to the initial voltage times e to the negative t over rc. We know the initial voltage during the time low starts out at 2/3 VCC, and we are looking for the time it takes for the voltage to drop to 1/3 VCC. So now we just need to solve this for t. Let's divide each side by VCC. Now let's multiply each side by 3. Multiply both sides by e to the t over rc. Remember, the natural log function is the inverse function of e to the x, so we can take the natural log of both sides to cancel out the e, and multiply both sides by rc. And since r represents R2, the time low is equal to the natural log of 2 times R2 times c. And that's one way to derive the first formula. Fantastic! There are other ways to solve this, and I'll show you another way in the next 555 math video. But for now, let's move on to the second formula. The second formula was time high equals the natural log of 2 times the sum of R1 and R2 times C. The time high occurs when the capacitor is charging through both R1 and R2. When the output is high, the discharge pin floats. Therefore, we can ignore its effect on the circuit. We are left with the capacitor tied to R2 on one side and grounded on the other side. R2 is connected to R1, which is connected to VCC. We can consider the threshold and trigger pins on the 555 as high impedance inputs. Therefore, we don't need to worry about their effect in the circuit. Because of this, we can redraw the time high circuit like this, where R represents the sum of R1 and R2, and V is the instantaneous voltage across the capacitor. Remember, the capacitor starts to charge when its voltage decreases to 1/3 VCC and continues to charge until it reaches 2/3 VCC. Let's use the V node as our junction for Kirchhoff's current law. The voltage across the resistor is VCC minus V, and Ohm's law states that the current through a resistor is the voltage across it divided by its resistance, flowing from positive to negative. The current through the capacitor is C dV dt, again from positive to negative. So, by using Kirchhoff's current law, we could say that VCC minus V over R minus C dV dt is equal to 0. The current through the capacitor flows away from the V node, so it is negative. Now we have the problem set up, so let's solve it. I'll first separate the variables. I can add C dV dt to both sides. I'll divide each side by C and multiply both sides by dt. Then I'll divide each side by VCC minus V, and I'll integrate both sides to get T over RC plus our constant of integration, K, equal to negative natural log of the absolute value of VCC minus V. I'll use the inverse function to natural log on both sides, noting that VCC minus V will always be positive. This gives us some constant k times e to the t over rc equal to 1 over VCC minus V. Note that e raised to a negative value is the same as 1 over e raised to the non-negative value, hence VCC minus V is in the denominator. I'll take the reciprocal of each side where k is some constant just like 1 over k would be. The new k will be a different value from the previous k, but still an unknown value. Now I'll add v to each side and subtract k times e to the negative t over rc from each side. Since k can represent any value, we can change the sign to positive. At time t equals 0, e to the negative t over rc will be equal to 1, so the initial voltage will be equal to VCC plus k, and k will be the initial voltage minus VCC. So V of t will equal VCC plus the initial voltage minus VCC times e to the negative t over rc. We'll save this for our next formula, but for this formula, the initial voltage will be 1/3 VCC, and we are looking for the time it takes to charge to 2/3 VCC. I'll divide each side by VCC, and I'll multiply each side by 3. 1 minus 3 is negative 2. I'll subtract 3 from each side and negate each side. I'll multiply each side by e to the t over rc. Then I'll take the natural log of each side. The natural log cancels out the e. And then I'll multiply each side by rc. Remember that r represents r1 plus r2, so we are left with the time high equal to the natural log of 2 times the sum of r1 and r2 times c. Now, the third formula was the initial time high equal to the natural log of 3 times the sum of r1 and r2 times c. The initial time high is the same as the normal time high, except we start charging from 0 volts instead of 1/3 VCC. So, we can start with the equation we saved and adjust the initial starting voltage to 0. We'll start by charging to 2/3 VCC. We can get rid of the plus and 0 and divide both sides by VCC. I'll multiply both sides by 3 and subtract 3 from both sides. I'll negate each side and multiply each side by e to the t over rc. Take the natural log of each side to cancel out the e, and multiply each side by rc. Knowing that r represents r1 plus r2, we have the initial time high equal to the natural log of 3 times the sum of r1 and r2 times c. Perfect. Now let's move on to the last formula that we'll derive in this video, which is the time high for the diode version. That time high was equal to the natural log of 2 VCC minus 3 times the diode voltage over VCC minus 3 times the diode voltage times R1 times C. So, the circuit for this will look much the same as for the standard time high, except instead of R1 and R2 in series, R2 will be bypassed with a diode. So, we'll have this here circuit with V being the voltage across the capacitor. We are still charging the capacitor from 1/3 VCC to 2/3 VCC. We'll use the V node for Kirchhoff's current law. The current going into the V node will be VCC minus V minus the diode voltage all over R1. And, of course, the current through the capacitor is still C dV dt. So, by Kirchhoff's current law, we have VCC minus V minus the diode voltage over R1 minus C dV dt. Now, all we need to do is solve this just like the previous formulas. So first, I'll separate the variables. I'll add C dV dt to both sides, divide each side by C, and multiply both sides by dt. Now, I'll divide each side by VCC minus V minus the diode voltage, and then integrate both sides. This will give us T over R1C plus some constant K equal a negative natural log of absolute value of VCC minus V minus the diode voltage. Using the inverse function to natural log, which is E, we get some constant K times e to the t over R1C equal to 1 over VCC minus V minus the diode voltage. Taking the reciprocal of each side gives us some constant K times e to the negative t over R1C equal to VCC minus V minus the diode voltage. Now, I'll add V to each side and at the same time subtract the K times e from each side. At t equals 0, the e turns into 1, and we get the initial voltage equal to VCC minus the diode voltage minus K. And K becomes VCC minus the diode voltage minus the initial voltage. Knowing that we are charging up to 2/3 VCC from 1/3 VCC, we now get the following. I'll divide each side by VCC and multiply each side by 3. Let's subtract 3 from each side and add 3 times the diode voltage over VCC to each side and simplify the 3 minus 1 in parentheses. I'll subtract 3 from 2. Next, I'll negate each side. I'll divide each side by what we have in the parentheses. I'll multiply the numerator and denominator on the left side by VCC. This will be the same as multiplying the left side by VCC over VCC, which is the same as multiplying by 1. Taking the reciprocal and swapping sides, I get this. And taking the natural log of each side gives me this. And finally, multiplying each side by R1C gives us our final result. Wow, that was pretty intense. We'll save the last formula, aka the monster formula, for another video since the Laplace transform really needs its own video to explain it. I really hope you enjoyed this video, even if you're just using it as a sleep aid, and hopefully learned something from it. Please peck at that like button, subscribe if you haven't already done so, and I'll see you next time, right here on Dr. Play.